We had two things for homework last night, practice question set number 27 and worksheet number 23. We're going to do practice question set number 27 right now and all of those questions. Number one says, experiments with cathode ray tubes led to the discovery of the, this should be a pretty straightforward question for us, right? What's the answer? It's going to be electrons, right? Cathode ray tubes led to the discovery of electrons, right? Because that charge to mass ratio was really, really big. The mass had to be really, really small, smaller than the mass of any atom. Number two, this is a bit of a tougher question. This is a good question, actually. Two says the property of cathode rays that provides the best evidence to suggest that they're not EMR. So we're not saying these are subatomic particles right now. We're just saying it's not electromagnetic radiation. What is it that best provides evidence for that? Yep. Yeah. Electromagnetic radiation cannot be affected by a magnetic field. Now, you could also say it can't be affected by an electric field, but that's not one of the options. So C is our answer there. 3, an experiment is designed to study the charge to mass ratio of hydrogen ions. Hydrogen ions, all moving in the same direction and with the same speed, are injected into a mass spectrometer, which is basically like a cathode ray tube, right? Except that we're using ions, in this case hydrogen ions, instead of electrons. But the setup of it is the same, just the charge and the mass would be different. We have an equation here that describes the radius of curvature of an ion's path. Well, if we're looking at the magnetic field and finding the radius of the ion's path, then we're looking at the main chamber of the cathode ray tube or of the mass spectrometer, as the case may be. So we'll say FC is equal to FM, or mv squared over r is equal to qvb. And then we're just going to rearrange this to solve for r. The r goes up, the qb goes down, and I end up with r is equal to mv over qb. So our answer would be B for that one. And number 4. Here's a good one too. A graph that shows the relationship between the radius of curvature of an hydrogen ion's path and the strength of the magnetic field. We always want to come up with an equation to describe it, and then we look at the equation and see which graph fits the equation the best. We're looking for the relationship between R and B here, between R and B. So in other words, as B goes up, the magnetic field goes up, R goes down, which means the answer is going to have to be either C or D, right? Which one is it? Which one is it, C or D? Yep. 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 Yeah, no, that's a really good way to think of it, actually. There's no absolute endpoint for this, right? As B goes up, R goes down, and R will go down to an infinitesimally small value, but not 0, right? So that has to be D. Does that make sense? As opposed to C. Now, next question. I really like this one. The manipulated variable in this experiment was modified in order to obtain the straight line graph as shown below. So instead of R versus B giving us this graph, we have R versus 1 over B giving us a straight line. Do we see how that happens? Do we see how we get a straight line graph from R versus 1 over B? Take a look for a second at this. Or take a look for a second at this one. We say Y is equal to mx plus B. The y-axis is R. M is the slope. The x-axis is 1 over B. Remember what the equation was? R is equal to mv over q times B. Look, if I plot this graph, R versus 1 over B, then I get this equation basically, right? R is equal to something times 1 over B. So by changing the manipulated variable B to become 1 over B, it actually straightens the line, which would be a good thing for us because it allows us to analyze it, right? We can't analyze this one. We can analyze this one because we know how to deal with straight line graphs. Okay, so this is what we got. And in this question, we want to find out the charge to mass ratio. So let's go at that with the technique that we've learned probably a dozen times now between labs and a couple of things that we've done in class here. Okay, we know what to do when we have a straight line graph, right? Y is equal to mx plus b. The y-axis is R, m is the slope, x-axis is 1 over b, and the y-intercept is 0 here. Well, now we got to come up with an equation either on my data sheet or derive an equation. It's going to be that one that we just saw. FC is equal to FM, which turns around into R is equal to MV over QB. Let's cross off things that appear in both. Cross off R because it appears in both. Cross off B because it appears in both. And we're left with the slope is equal to MV over Q. Agree? We can all do this, right? We can all get to this step. Now, what were we looking for? Q over M? Well, let's rearrange this. We got M over Q. Let's rearrange it to get Q over M. So the Q is going to go up, and the M is going to go down in order to get Q over M. So Q times the slope over M equals V. And if we take the slope over by dividing, we get Q over M is equal to V over the slope. You want to find the charge to mass ratio of this? Let's go slope. So let's go V divided by the slope of this graph. Now let's go to our options here. Speed divided by the slope is our answer. How many people got that one? Okay, that's not bad. Hey, that's a tough one. We're going to see a graphic question on our exam. We're going to see a question where we have to use the technique that we just used. But I would say that I think at least this is probably one of the harder ones that we've seen. I don't know. I don't want to say it's the hardest, but it's one of the harder ones that we see because of the whole, I don't know, the M over Q, and you got to get Q over M and so on. But if you follow along with this, it's really just the same technique that we've always used, right? Equation from your graph, equation from your data sheet, or in this case, derive it. Find out what the slope means, and then find what you're looking for. You got M over Q, solve it for Q over M, and we're done. Yeah, it was. Yeah, you're right. It was. Yep. Yep. Good. Good. 6, to determine the speed of charged particles in a cathode tube, Thomson balance force is produced by, this would be the electric field and the magnetic field. If it was an electric field and a gravitational field, this would be the Millikan experiment, right? Millikan experiment. Thomson's velocity selection chamber would be electric and magnetic, Fe equals Fm. And that's what we're going to do in question number 7. In fact, when we're asked to find the speed of the alpha particle, is analyze the velocity selection chamber where Fe equals Fm. We're going to say Q times E is equal to QVB. Q's cancel. E is equal to V times B. Now, we don't know what E is, the electric field is, but we can replace that with delta V over delta D. We got delta V, we got delta D, although you do want to make that in meters, not centimeters. And you got B, the magnetic field strength, so you just solve for V. And I think when you do that, it works out to be, was it D, 3.41? I think it was. Times 10 to the 5 meters per second. Let's take a look at our second set of homework now, which was worksheet number 23. I want to do 2 questions on here, number 3 and number 5. 3 says, what potential difference would be necessary to balance an oil drop with 5 excess electrons on it when the mass of the oil drop is 4.89 and they're 5 centimeters apart? Okay, we have 5 excess electrons, which means the charge here is going to be negative 8.0 times 10 to the minus 19 coulombs. Right, the charge of 1 is 1.6. The charge of 5 is 5 times that, or negative 8.0 times 10 to the negative 19 coulombs. We've got a mass of the oil drop. We've got a distance between the plates. We're looking for the potential difference here. This oil drop is suspended. The forces are balanced. So that means we can set Fe equal to Fg, not Fe equal to Fm, because that would be the velocity selection chamber of the cathode ray tube. Fe equals Fg. Q times E is equal to M times G. Now, we're going to replace E, the electric field, with what? Electric field between 2 parallel plates is delta V over delta D. We've got charge. We've got the distance between the plates. We just got to make sure we put it in meters. We've got the mass. We've got G as gravity is 9.81. We solve for the potential difference there. And when we do solve for the potential difference, mgd over Q gives us 3.00 times 10 to the 3 volts. We okay there? Some of you may choose to go with this, solve for E, and then set it equal to delta V over delta T. Either way is okay. How many of you guys did that? Solve for E and then set it equal to delta V over delta T? Okay, perfect. How many of you guys just did it the way that I did it here and plugged the expression in? Okay, just as perfect. Okay, exactly the same amount of work, exactly the same answer we get out of it. Okay, let's take a look at number 5 as well. Again, number 4 is real similar to question number 5. So I ask you if you had trouble with number 4 to go back and try that again after we go over number 5 here. 5 says, an oil drop with this mass accelerates downward at 2.5 meters per second squared. Why am I doing this? Why am I circling the acceleration in red? Yep. Logan? Or yeah. Yeah, it's a downward acceleration, so we're going to make it a negative value. Calculate the charge in the oil drop at the distance between the plates is 10 millimeters, and the potential difference between the plates is 538 volts. We know in one of these problems, because it's accelerating, we know that F net is equal to the sum of the forces. Or MA is equal to QE plus M times G. Let's sub in some numbers here. The mass is 3.50 times 10 to the negative 15 kilograms. The acceleration is what? Hamish? Good. Negative 2.5 meters per second squared. Q is what we're looking for. The electric field strength, we don't know the electric field strength, but we do know that it's delta V over delta D, right? 538 volts divided by 0.010 meters. Remember to put the vector sign over top of the E, right? Don't want to get it mixed up with energy. I can't tell you how many people yesterday between the 3 classes mixed up energy and electric field. It happens a lot. You don't mix the two up. Plus the force of gravity, which is 3.5 times 10 to the negative 15 times 9.81. What about signs here? Gravity positive or negative? It's negative, yeah, because it's downwards, right? Now that we've subbed numbers in for electric force, is it positive or negative, upwards or downwards? Ooh, good one. Is the electric force up or down? Is the electric force up or down, Kenway? How do you know? Well, not always. Sometimes the electric force will be in the same direction as gravity, and it accelerates downward. Sure. Okay, but we don't know which way the electric field is, though, unfortunately. If we knew which way the electric field was pointing, we'd draw a diagram, and it would be really easy. Well, not easy, but we could determine which way the electric force is based on the negative charge. Does it actually say? No, we don't even know that it's a negative charge, actually, do we? No, we don't even know that. Yeah, so we couldn't do that. Go ahead.
We know that it's going up, the electric force is upwards because the acceleration is less than.
Good, good. If it was just gravity, it would accelerate downward at 9.81. If it was gravity and electric force pushing downward, it would accelerate downward at more than 9.81, right? But it accelerates downward at less than 9.81. So there has to be something to counter gravity. That's going to be the electric force pushing upward. So it is going to be positive. Okay, calculate this number. Calculate this number. Take it over by adding. Calculate this number. Take it over by dividing. And we should end up getting a value here when we do that of 4.76 times 10 to the negative 19 coulombs. Now, when we do that, we get an answer like that. We don't know for sure that we're right, but if you get a number that's that close the 3 elementary charges, you can be relatively confident that you're right. Okay, you can be relatively confident that you're right. Because if you had made one of these signs wrong or something, you would have gotten a number that probably, in all likelihood, was not a whole number multiple of the elementary charge. Yep. No, not necessarily. It could be 10 to the negative 18, 10 to the minus 17. It's probably not going to be like 10 to the minus 6, and it definitely won't be 10 to the positive something. It's usually, you know, if it's 3 electrons, it would be 10 to the minus 4.8 times 10 to the minus 19. If it was 30, it would be 4.8 times 10 to the minus 18. If it was 300, right, you're not going to have 3 trillion. You might have 300. All right.